Welcome to Faster Apps Faster. Hope you guys had a good lunch and you're ready to process some information about the GWT compiler. So my name is Ray Cromwell, and I work on the GWT compiler for the GWT team. And one of the things I hope to show you today is how the GWT compiler works, how it actually makes your JavaScript faster and smaller, and then sort of maybe to give you a couple of tips about how to help the compiler along a little bit. And then we'll talk about how to make your builds faster. So if you want to follow along, there is a bit.ly link for you, bit.ly/io2010-gwt2. That will be a Google Wave where there's some live note-taking, and I think you can ask some questions there. So as I said, there's going to be two things covered in this presentation. One is building faster apps, how the GWT compiler actually helps your apps execute faster, load faster, and so on. So I'll kind of get into the details of the compiler in a way maybe that hasn't been explained before. And then the second part is I'll try to help you actually speed up your compilation so that you're waiting less for your builds to actually happen. So here's the inspiration for this. I don't really think I need to preach to the choir too much, but latency matters. And if you saw Kelly, I have a call there. If you saw Kelly's presentation on SpeechRacer earlier, you really know how much latency matters. But there's a monetary reason why as well. Amazon actually presented at a web conference last year and reported that for every 100 milliseconds of latency, they lost 1% in sales. So that's real money. Likewise, Google actually did a focus group study of people using the browser, and they found out for every 500 milliseconds of latency it takes for the search results page to come back, they would lose 20% of their traffic. And that's huge. So we definitely want to speed up the rate at which your apps can load and return results to the user. And GWT helps a lot with that. So here's an example. If you were a user who started out in 2006 on GWT 1.3, and all you did was simply recompile your application, you made no other changes to your code, just sort of downloaded a new SDK and recompiled it, your JavaScript got 30% smaller. So you didn't have to do any work at all. And I think that's pretty good. And what we've done over time is we've continued to iterate on the GWT compiler and try to make the code smaller and faster so that all you have to do is simply update to later versions of the compiler, and we make your web app just run faster. Here's another measurement. This is between GWT 1.7 and GWT 2.0, startup time latency, how fast it takes for your app to first show to the user. And this graph's kind of hard to read, but GWT 1.7 is represented as a 1.0 factor. On Safari, if you recompiled with GWT 2.0, the speed up was 2.5. So that means the latency went down by a factor of 2.5. So if it was 250 milliseconds startup, it went down to 100 milliseconds. Likewise, for Firefox, the improvement wasn't so dramatic, but it did get a factor of 1.25 improvement. So with that said, let's talk about what the GWT compiler is. So a lot of people you're not really sure what it is. They just think, okay, it translates Java to JavaScript. Maybe it maps, a Java method directly to a function declaration in JavaScript. It's just a straight one-to-one translation. And actually, it's not. The GWT compiler is a totally classical compiler, just like your C compiler or your Pascal compiler or things like that. It aggressively optimizes the code and really changes it, moves it around a lot. Moreover, it actually produces multiple executables. So it's kind of like a cross-compiler. Like if you were cross-compiling for x86 and ARM, only the target platforms are not two different CPUs, they're two different browsers, or mobile, or different locales like Chinese versus German. And just like your C compiler, it now has a linker. So there's additional steps you can do with the artifacts that are produced by the compiler, like repackaging them for different things. Like let's say you wanted to install a GWT application as an Android application that appears on the menu. You can write a linker for that. So here are some of the core concepts of the compiler. One of the most important ones is this thing we call permutation. So basically, the compiler has the capability, as it's compiling, based on rules that you write, to basically assertion replace classes. So maybe you've got a class and you called it payment service. Well, maybe you want the GWT compiler to replace that for different patterns. Maybe on Android you want to use protocol buffers, and on GWT you want to use RPC or something. Well, the compiler can do that, and it's called what we call deferred binding. So it's the ability to sort of do dependency injection at compile time instead of runtime. And the interesting thing is that after the replacements are done, the compiler sort of looks at the all the permutations that have had the substitutions done, and for every unique substitution, it does a separate compilation. So you get a different executable in a sense. Here's a more famous example. This is in the GWT user library. So GWT has this class called DOM, which delegates to DOM-impl. And DOM-impl basically knows how to do things like append children to the DOM, create elements, attach event listeners, and so on. It's the API for interfacing with the browser. But because different browsers, as you know, have different ways of interacting, like IE uses attach event, and every other browser uses add listener, add event listener, you need different implementations of that. And the traditional way it's done in most AJAX libraries is you have like a test. You say like, if element.add_attach event, then it's the IE version, and if it's else, it's HTML5 version. And that means that when you send your application to a Firefox user, it's got all this IE code in there that's never executed. It's just tested for but did not run. What we do in a GWT compiler is we say, look, when a compiler is compiling the thing, if you're compiling for IE, let's just only include the class called DOM-impl IE or DOM-impl IE8, which includes all the IE-specific versions of those methods. And then if you're on Firefox or WebKit, let's substitute in a special version for those, in which case you're producing now 2 or more executables, 1 for each browser. But they're smaller because each one doesn't have to know about the other browser's edge cases. But there's more to this than just that. What this does actually is it permits the compiler to make better optimizations. So for example, if you had a class called animal and had 2 subclasses, cat and dog, and let's say in the Safari browser you instantiate a cat, and in IE you instantiate a dog. Well, what happens is the compiler, when it compiles these 2 separate permutations, only one of the classes is instantiated in each. So the way the compiler sees it is, an animal is always a cat. There's no other type of animal but a cat, and likewise in the other browser. So it actually permits the compiler to replace all of those polymorphic method calls that may be overridden with just a direct inline call to a cat method. So that's sort of the preliminary. We get that out of the way. Here are the major phases of the compiler. So there's 5 of them, and the first one is called precompile. So what precompile does is it basically looks at the source code in text form that's on your disk, sucks it all into the compiler, and creates intermediate data structures like abstract syntax trees, and then hands it off to another phase. Or, as you'll see later, it can actually send it out to a network where it can be distributed. You can build it in a distributed build. So that phase doesn't do much except for like parsing and some other fix-ups. The next phase is more important. That's the Java optimization phase. This is basically where the compiler is saying, I know about Java, I know particular things about the Java type system, so I'm going to do optimizations based on what I know about Java. But of course, there are some things in a JavaScript application that a Java optimizer wouldn't know about, like closures, function redefinitions, property lookups, and things like that that just don't exist in Java. So there's a separate JavaScript optimization phase that works on a JavaScript AST. This phase actually also does what many of you might be familiar with, what's called code splitting in GWT 2.0. Finally, after you take that JavaScript and you do all the optimizations on it, you have to get it back to text as a .js file. So when you serialize it out this text, you want to do minification and obfuscation and all kinds of compression. So there's actually optimizations we do purely on the text alone. Like we don't even know what the code is. We're just doing actual text transformations, and I'll show you some of that later. Finally, there's the linking stage, what I mentioned earlier, which is how you package it all up at the end. So let's go on to talk about Java optimization. So there's many more than this, but these are some of the most important ones. The first one's called type tightening. The second one's called what we call statification. It's sort of a mouthful. It's converting non-overridden methods to static methods. Finalizing, pruning and dead code elimination, and method call inlining. So type tightening, what is it? So before I use the example of subtyping animal in 2 separate permutations, but even if in one permutation you have 2 classes, sometimes the compiler can reason that there's only ever one that's going to be used in a particular circumstance. So here we have animal, and it has a cat and a dog subclass. And you have an assignment here, which is animal A equals new cat. If dog is never instantiated by a new call in this method or in any other method, then compiler will say, well, look, I know no one ever created a dog, so I'll just change that left-hand side of that equation to be a cat type. Likewise, there's a method there called public static dog get animal, right? So the return type of this method is always a dog. So if you were to say object O equals get animal, the compiler would say, well, hey, that thing always returns a dog, so let me fix up the type on the left-hand side to a tighter bound, right? So that's why we call it type tightening. And this helps a lot when we get to inlining. So staticifying methods, this is kind of a hard thing to pronounce, but basically what this does is here you have two methods in animal. One is a public string to string, and it returns a name field, and it's not overridden in any subclasses. The next method is public void speak alert, and this one is overridden in the cat subclass. So since the compiler knows that toString is never overridden, it's fundamentally not polymorphic. So the compiler can say, okay, well, I'm going to actually just take that off the object and make it a global top-level function. And the result is what you see at the bottom, which is public static string toString. And now what would normally be the this pointer for the object is passed in as an argument. And this has a lot of benefits. For example, like top-level functions actually tend to execute faster and in Chrome and V8, so there's sort of some JavaScript VM things going on. But also, it actually allows the compiler to inline it, because since it's not polymorphic, it actually knows that there's only one method toString for animal types ever. It doesn't matter if it's a cat or a dog or whatever, it's always x.name. So it just will just inline it as x.name. So finalizing, sort of an addendum to that, we notice that a method's never overridden, a class is never subclassed, or a variable is never reassigned. We'll just change it to be final. We'll just add a final qualifier for it. And that helps the compiler out, because if it knows, let's say, a constant, like int x equals 10 is final, then later on, when there's a reference back to that variable, it can just go, well, that thing's never being assigned and different value. It's just a constant. So it can actually just replace a later reference with x with the actual number, thereby eliminating a variable assignment. So pruning by far is the most important thing in the GWT compiler. And basically it kind of works like code garbage collection. What we do is we start out at the entry point of your program, and we sort of trace through in the compiler. And we determine every possible bit of reachable code that could ever be touched by executing your program from the entry point. And when we do that, at the end we have a collection of what's called the live methods or the live fields, the live classes. Everything else we just throw away. So the result of this is if you're using GWT and you're using a bunch of libraries or whatever, you usually don't pay for code you don't use. You could have 500K of libraries, and you call one method. You don't incur the cost of compiling all that JavaScript into your output application. Dead code elimination is a phase of the GWT compiler that's, I think it's somewhat poorly named. It really should be called static evaluation or compile time evaluation, because what it does is it looks at the code and says, if there's some piece of code that I know just by looking at it that I could replace it with the answer of evaluating that at compile time, then I'll do it. So for example, if you had an expression like false end-end expression, the compiler can just go, well, that's always false, because the right-hand side will never be evaluated, so it'll just replace the left-hand side with false. Or maybe you have if false, so you have like if debug, and debug is a variable somewhere, and you have a bunch of debug code. If you declare that at the top level of your program is like debug equals false, the compiler will just make all of those debugging statements go away. Constant folding, if you're doing a bunch of string concatenation, every time there's two constants that are side by side, the compiler will just go ahead and add those together, so it won't incur any runtime costs for string concatenation. Likewise with numbers. And there's just a whole bunch more that it does. It can convert postfix ops that are never assigned into prefix, and that might not seem very important, but it turns out that it helps out the JavaScript JITs a lot when they're doing a bunch of increments, like in a loop. Constant propagation I already kind of covered. And here's an example of what you get. So last year I presented this library called GWT, which was a re-implementation of jQuery in GWT. And the library is actually about 300 kilobytes of Java source on disk. Here I have gzipped it to kind of make the comparison fair, but the source code of this library is 50 kilobytes gzipped. And I wrote a sample application that sort of applies a bunch of progressive enhancement to a page, but I only use a couple of the functions in the GWT library, like altering CSS or doing hover or something like that. The resulting application compressed is 780 bytes. So the compiler threw away 99.99% of that code, and all you're left with is just a couple of inline functions that actually got called. And you don't tend to get this situation when you're using pure JavaScript, because you don't tend to know ahead of time what methods were going to be called. So you actually ship down the entire JS with all of the functions, because you don't know ahead of time. But because we have a compile step, the compiler gets to see all of the code that is expected to be sent to the user ahead of time, so we can actually make that determination. Here's another example. This is sort of a graph showing that how big your application will be as you start to call more methods in the GWT widget library. So if you start out with nothing, you get this little empty one down there. I know this chart's kind of hard to see, but it's not really relevant what those bottom axes labels are. But basically, each one of them is another widget you're using, text box, tree, and so on. And as you add each widget, the size of the application output goes up a little bit. But as you can see, it kind of tapers off because there's a lot of code sharing that happens between widgets. They use the same base class. They use the same Java util collections. So it doesn't grow without bounds. But if you want to actually make a small application, you can. You just have to be a little bit careful about what methods or what widgets you're going to use. And that's what I did in jQuery. So method inlining. So this is another really important optimization in GWT. And what it basically does is what it says. If you see a function like add tip, float bill, comma float rate, and it has an expression return bill times 1 plus rate, and if the compiler can actually determine what the target method is, like it's not overridden by 5 different implementations, it will just take the parameters that you see at the call site and substitute them for the actual variables in the body of the method and then replace that at the call site. So you see that the add tip 100, 0.2 becomes, after inlining, 100 times 1 plus 0.2f. But then, because of that dead code elimination phase, the compiler goes on and says, hey, everything there is constant. So it actually just rewrites that as the answer, which is 120. So if this was a real application, what you can see is actually the add tip method got totally eliminated. It never even made it in the download to your user. The Java method inliner is not perfect. It actually has a lot of restrictions, but some of those are for good reason. But it does 3 things really well. One is that it reduces most of the Java getter-setter call. So when you tend to program in Java, you tend to have property getters and setters. And the inliner definitely will eliminate almost all of those because they're usually not overridden and they're usually small. It tries to avoid bloating the code, though. So if the method's more than a couple of lines long, it won't inline it because it will tend to make the JavaScript bigger, and that's one of the main things you want to guard against. Finally, it enables optimization stages to work better. So for example, if you've got like one method and it's calling another method, it's going to pull that other method into this method, and then the compiler kind of has more context to see when it's tracing through the code what's depending on what, so it can eliminate more because maybe there's some dead code in there that got pulled in. So after it's finished with the JavaScript optimization stage, it goes on to do, sorry, the Java optimization stage, it goes on to do JavaScript optimization. So it takes the Java code that's optimized and it dumps it into a JavaScript data structure. And then it performs many of the same optimizations, so static evaluation, so the same things you saw for like constant expression elimination and so on, it does it in JavaScript as well, because there were probably some things it didn't catch, like variables that came in from JSOs and things like that, that the Java part of the compiler does not know about JavaScript, so it can't do that part of the work. The inliner is also in there, and there's a reason why you want to have a JavaScript inliner, is because JSON methods don't get inlined by the Java part of the compiler because it doesn't know about JavaScript methods. Likewise, if you have like a method that has a closure in it, you can't really inline it because the closure captures the scope of where it's declared. And if you basically inline the body into another scope, you've changed the meaning of the code. Unused function remover is like a pruning. And code splitting, of course, people have probably heard of if you're a GWT user. I already kind of covered the JavaScript inliner. So, but here's the result. This is probably the thing you're more interested in. So when you do inlining, although V8 and Nitro and many of the other JavaScript engines, like TraceMonkey, whatever, they're getting pretty good at this. They're still not perfect. So when the compiler does inlining, it still actually helps the performance of these advanced JavaScript VMs. And in this case, what we have here is a demonstration of capability detection versus polymorphic versus inline. And what this means is, let's say you had some particular piece of code that had to run differently on different browsers. So on IE, maybe you did like, if element.attach event, then some bit of code, else some bit of code for Firefox, and so on. Another way you could do that, of course, is you could make a different object and have it overridden for IE and have it overridden for Firefox, like, attach element as a method on something. That's the polymorphic case. And then the third case is inlining. So as you can see, the difference between capability detection and polymorphic is not that different on the modern browsers. But actually, when the GWT compiler inlines these things, it results in a 10% performance improvement. And there's a more dramatic example of this. Kelly Norton, who did the measured in milliseconds talk earlier, ported the SunSpider browser benchmarks from JavaScript to Java and let the GWT compiler have at it. And this is the result. GWT is in yellow, and the JavaScript version is in blue on the same browser. And you can see there's some dramatic performance improvements in some of these benchmarks, purely because of the optimizations I outlined earlier. So GWT produces code that usually can be made actually smaller than what you write by hand, but it actually produces faster code, and that's the more important thing. This is probably an even better one. This is GWT query. It's my jQuery port, so I rewrote the CSS Selector Engine that jQuery has in Java for GWT. And then I had GWT have at it. This is a comparison of Prototype, Dojo, jQuery, and GWT query on the slick speed CSS Selector benchmark that they all use. And as you can see, Prototype came in at about 3,800 milliseconds. Dojo was about 1,200. jQuery was about 600. And GWT query was about 400. So GWT basically produced code that was faster than the best JavaScript ninjas in the industry could produce by hand. And I think that's something to say. So after you've done JavaScript optimizations, we have to get it on disk so it can be sent back to your browser. And this is the text-based optimizations part of the browser. So the first thing we're going to do is we're going to take that tree in memory of the JavaScript program, and we're going to serialize it sort of to text. But as we're serializing it, we can remove all extraneous white space, semicolons, and parentheses, and so on. So a common thing, of course, and I didn't even know this until I started doing this, but like you can leave off parentheses when you're calling JavaScript constructors that don't take arguments. So if you have new foo, you can actually change it to just new foo without the parentheses. That actually dropped the size of GWT applications by about 1%. And that's a pretty good improvement for such a small change. The compiler also knows a lot about the JavaScript language and the precedence of operators. So, you know, if someone accidentally put extra parentheses around an expression like A plus B times C, because they weren't kind of sure whether or not A plus B was going to be evaluated first, the compiler will go ahead and just remove that. But the next stage, of course, is more important. The compiler performs aggressive obfuscation, far more than what you'll get in like YUI compressor or any of the other JavaScript libraries. And the reason why it can do that is because it knows every single method that will ever be called from the start of your program. So it knows whether it's public, private, who's using it, and so on. So it's free to totally rename everything, and I mean everything. A lot of the other minifiers don't, because they're not sure if a given method, like, you know, create widget or whatever, create a slider, is actually going to be called from outside the library, or whether it's just an internal function only. So the compiler knows a lot more information about what's actually called. So pretty much in a GWT program, when it's actually compiled and it's on disk, there's almost none of the original identifiers are present, and everything gets changed into the 1 or 2 character variable names. The interesting thing, though, is when you do this to a GWT program and you look at the output, you'll see a lot of functions that look identical, like functions duplicated over and over again, like dozens. And you're saying, like, why does someone write the same function like 10 times? And it turns out what happens is that every setter method or getter method you write, after it's obfuscated, will tend to look identical. So if you had, like, on an employee object, let's say you had set first name, and it was saying this.firstname equals something. And then on, like, a car object, you had, you know, set model year, you know, this.model year equals something. Well, after you compile those and obfuscate them, they look identical. They both say, you know, this.x equals y after obfuscated, because they get the same identifiers assigned because they're just methods. So we give them a first available letter, which might be A or B or C. So you have, like, you know, this.a equals b or something. So because that's actually the compiler does this, we can just simply do a simple search and replace. So what we do is we take every method body and we just, you know, sort of store it aside and compute a hash of it. And when we're about to emit another method, we check to see if it's already been emitted. If it already is, then instead of emitting that method a second time, we just emit a reference to the first one. So as a result, if you have, let's say, 20 beans in your, you know, application, the first field assignment property setter will be the one function for all 20 of them. It will just be a static method that just applies to the bean. Likewise for the second, and so on. So it actually I think it reduces the output size by about 2 to 5%, depending on how many property setters and getters you have. Finally, this is probably an interesting one. I was doing some research on trying to make gzip work better. Like, how can I tweak the output of the compiler so that the compression ratio goes up? And it turns out that there are actually some things you can do. If you take the code and you sort it such that functions that sort of only differ by a few characters are closer together in the output, then the gzip algorithm, when it's searching backwards in the program to look for a match, sort of when it's doing its compression, so it actually can find it easier because it gives up after a window of like 8 to 32 kilobytes. So if your application is like 100K and there's a function called foo, and it's looking backwards for another one that's sort of similar to foo, so it can kind of compress the two together. If it's further back in the file than 8 kilobytes or 32 kilobytes, it gives up. So it never sees the other one it could have used for better compression. So you simply bring the functions that are similar closer together in the output file, it boosts the compression efficiency. And there are some other reasons why that happens too, but they're more complicated. But here's an example. If you had something like bat, cat, rat, bat, cat, rat, bat, cat, rat, and we simply reordered those, and those represented functions, we simply reordered those, so it's bat, 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 cat, 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 rat, rat, rat. You see that the sort of the redundancy is more clear to the compressor. And this, when I implemented this, it sort of, in some cases, it's just maybe a 1 or 2% compressency increase, but I've seen it go up to 15% better gzip compression. So it depends on the application, but it's kind of a unique thing that the GWT compiler does. So that's it for how the GWT compiler works in terms of the optimizations. What I wanted to talk about here was to sort of give you some advice on how to change your code so that the compiler would work a little better. But on second thought, when I started to think about it, I actually don't want you to do that because it's our job to not hamper your coding style to fit the compiler. It's our job to make the compiler better so that you can just code the way you want for maximum productivity. So rather than give you a bunch of micro optimizations, I just want to give you some general principles here. One is, because of that static evaluation thing I showed you earlier, where if you have like if false, it just eliminates code. One of the best things you can do is if you have some bit of code that maybe only runs on one browser or runs in one locale or runs, let's say, in debug mode versus production mode, you can put it behind a guard. In this case, I'm using a login example. So let's say you have you want to do some logging code. If you put it behind something like if log.isLogin enabled, then what you can do is you can use the deferred binding mechanism I talked about earlier, where the compiler can substitute the implementation. And you could have it such that in your debug permutation, the compiler will replace that log class with one where isLogin returns true. So the compiler will not eliminate the debug code in that compile. But for the production version, you can substitute a version where it returns false, in which case, if you went to town on logging statements and you've got like hundreds of thousands of logging statements all in your program, they just all go away, and none of it shows up in your production case. So that's one tip. The other thing is, in general, if you do have code that's intended specifically for different locales and browsers, you do use the deferred binding mechanism, read up on it. So static initializers are a potential source of problem. How many people know what a static initializer is? I just want to get some hands. Yeah. So if you have a static field on a class, you know that when you reference the class, the compiler, well, the Java VM has basically already run the initializer that you might have had on that class. Like if you had like, static hash map equals new hash map, right? Well, the compiler has to ensure that if you ever call like, object dot hash map, you reference that field, it has to make sure that initializer was called first. So the GWT compiler has to be faithful to those semantics in Java. And the way it does that is whenever you have a static method and you call it from another part of your GWT code, GWT will insert another function call in front of your call at the call site, which is called CLinit, which will ensure that first it called that initialization to set up that field before the method is allowed to execute. And the second time it's called, of course, it won't do the initializer. It's kind of like it will check to see if it's already been initialized and then won't do it. But that bit of code is always there. So every time you call a method, first it's going to check to see if that field got set up, and if it didn't, it leaves it alone, but it's still bloat. So my advice would be is that Stay away from, well, not use singletons, but be careful when you use singletons and static fields, and sort of opt for objects and lazy evaluation where you can. It tends to help the output a little bit. In general, if you keep methods small and functional, by small I mean just a few lines long, and by functional I mean they don't mutate much, or they don't mutate anything at all. So like they just kind of take the parameters, perform some computation, and return it. The compiler will be able to do a better job because it can reason better about pure functional code than about code that mutates a bunch of stuff all over the program. And finally, use code splitting. So code splitting is too complex for me to go into in this presentation, so I hope everybody is aware of it. But code splitting can dramatically reduce the size of your application. For instance, for Google Wave, it reduced it by a very significant factor, from like a megabyte application to like 100K for like the startup. Okay, so here are some tips, though, that you can do that don't rely on you changing your code. It's kind of tips that you can do that you can tweak the compiler to make the output smaller. So in GWT 2.0, we introduced this new thing called stack stripping. So GWT 2.0 had this ability to turn on stack emulation traces for IE6. Where this is basically like if you get an exception thrown in JavaScript, we will actually show you a Java stack trace. So you'll actually be able to know where to go in your code to find out what caused the problem on IE. On other browsers, actually, on like Chrome, WebKit, and so on, they actually have some built-in stack trace functionality. But this relies on the fact of keeping the original function symbol names in the source code, because otherwise you won't know what the function is. It'd be called like function X, right? So what was added was this new thing called stack stripping mode. If you turn on stack stripping mode, what it does is it tries to rename as many functions as possible in your program to anonymous functions, meaning they have no identifier at all. It's just like function, open, close parenthesis. And the benefit of that is that it frees up the obfuscated identifier table. So the compiler is trying to assign 1 or 2 character names to everything to make your JavaScript as small as possible. So for every function that's able to change into an anonymous function, that's another extra identifier that can be used somewhere else for a variable name. So it actually tends to reduce the code by about another 5%, depending on how many methods can be anonymized. Another thing the GWT compiler does is it tries to faithfully allow you to call things like the java-lang class.getName method and getPackage and so on. So most people don't need to do, because GWT doesn't allow dynamic class in it, so most people don't need to access the java-lang class method because class, because we don't have reflection and things like that at runtime. So you can, for production, you can turn on this flag called -x disable class metadata. And if you do that, the compiler basically doesn't even keep the names of classes around in your program. It basically just renames every class to be like class 1, class 2, class 3. That also significantly reduces the size of the program. Finally, a lot of the semantics that people use for debugging GWT applications, like getting class cast exceptions or array store exceptions and things like that, are not needed for production app, because the production user is not going to know what to do with it anyway. If you sent some guy's reading Gmail and he gets a class cast exception, what's he going to do with it, right? So you can add this parameter called -x disable class cache checking, and the compiler will remove all of the runtime cache checks all throughout the program, making it smaller. So if you're using GWT RPC, there's a relatively hidden module that not many people know about called Remote Service Obfuscate Type Names. So when you perform a RPC call in GWT to the server, it serializes your Java classes on the client side and sends to the server and vice versa. So when it's communicating with the server, it has to tell it, hey, this is an employee object, this is a array list object, and so on. It has to say what the names of the types are it's sending over the wire. But it actually doesn't need to have them be the same names that they are in the server-side VM. So if you turn this on, it actually will obfuscate the actual names of the types that are being sent over the wire. And this actually is useful for 2 things. One is it will make the RPC payload smaller, and it will make the actual code of the GWT application smaller. But 2, for security reasons, you might have some classes on your server side that you don't want to expose to the client. So this will actually make it so those don't show up in the RPC payloads. If you have adopted GWT 2.0 and you've started to use UI Binder and Client Bundle, you know that there is the ability to have GWT actually compile and apply optimizations to CSS style sheets. It can minimize and combine properties. It can collapse combinators in CSS and all kinds of like useful things. But it actually can obfuscate class names and a lot of other things as well too. So if you turn on this property, GWT will get a lot more aggressive about how it obfuscates all your CSS class names. So it's relatively useful if you're using like UI Binder or Client Bundles. When all else fails and your application is still too large and you want to make it a little bit smaller, one of the first things you could do is try to eliminate RPC. Now RPC does tend to add some bloat to your application, and if you've got a backend that's written in like another language like PHP or Python or so on, and you're using JSON for your payload, or you're willing to use JSON, moving from RPC to JSON can buy you some space. Likewise, you can use a thin client library like GWT Query. Instead of using GWT widgets, you progressively enhance things like you would do if you were doing JavaScript. There are some upcoming optimizations this year that should be making the GWT compiler a lot better. We're making the inliner a lot smarter about what it can do, what can be inlined, so your code should get a little bit faster and hopefully a little bit smaller. There's a totally new optimization framework that's being put into the compiler called GFlow. It's a new data flow optimization framework, which some of the most sophisticated C compilers today are using. So this will allow us to do a lot of amazing stuff like object field inlining. So we could do things like if you have an iterator over a collection, we can change that into a for loop and get rid of the iterator object in Java and just make it like for I equals 1 to 10 on an array list. So the iterator can just go bye-bye. Enum optimization. So if you've used enums in Java, a lot of people have complained that they tend to add bloat because each value object in an enum, the way Java translates it, becomes a separate subtype of the enum. It's like a separate class. So if you've got an enum and it's got 100 values in it, you kind of have 100 class declarations in your output. And that's not really that good, especially if the enum's only really being used as sort of a type-safe number in a sense, right? Like you're passing, you're using a switch case statement on or something. So some of the new optimizations we're doing is things like we detect this and we eliminate the enum and just turn it into an integer from 1 to 10. So we replace all the enums with just numbers. But our end goal is to dramatically reduce the weight and cost of the Java runtime environment that's used by GWT. And hopefully that will be coming to a GWT compiler near you in the future this year. So that covers the compiler, and that's sort of quite a lot to take on. But all of this stuff comes at a cost. So if we're a JavaScript programmer, or maybe you've adopted GWT, you might have realized that your compiles are taking longer. Things have you're waiting around, you're checking your Twitter account while the compile's running. And there's a reason for that. It's not because we don't realize that the compiler has gotten slow over the years. The reason why it's like that is because we started out focusing on latency, on the performance for the end user. So, we looked at things and we said, if we can make the application 5% smaller, we can shave off like 100 milliseconds off the startup or something like that, but it takes you an extra 30 seconds to compile it, we're going to do it. And you should not feel too bad about it because look, you're spending 30 seconds of your own time compiling it, but a million of your users are getting back 100 milliseconds of their time. So it's a good trade-off for your end users because those are the ones who are paying the bills. However, we do realize that it kind of impacts your productivity a little bit. But in most cases, if you're a hardcore GWT developer, you're probably using, or if you're not, you should be using dev mode because that will reduce most of your compile, edit, debug cycle to about 1 or 2 seconds. The problem is that if you're in a larger organization, not everybody is going to be using the GWT toolchain. For example, you might be building a GWT application that's kind of like a portlet that's like part of a larger enterprise dashboard or a larger application, in which case some guy just editing JavaScript or CSS off in the corner is waiting for a continuous integration build of the GWT compiler to get like the latest stuff so you can copy it over and run it. So not everybody who depends on GWT code is actually a GWT user or runs GWT tooling. So we realized that, and with that in mind, let's see if we can speed up the GWT compiler for you. So here's some of the things I recommend to do. Some of you might already be doing this, but hopefully there's a couple of things in here you haven't thought of. First, use two modules. So normally you might have a GWT module like myproject.gwt.xml. So create another one. Call it like myproject.dev.gwt.xml. And what you're going to do is, one of them is going to be your full production build, all browsers, all locales, no debugging, no class metadata, stripping out everything we possibly can to make it as small as possible. Aggressive optimizations turned on. The second one is going to be the dev build. That's going to have all the logging, all the debugging, pretty mode, no obfuscation, but it's going to be tied to a single browser and a single locale. In this case, what I'm showing is I've forced the compilation to only compile for Safari and to only compile for English. What that does, it limits the amount of separate executables the compiler has to compile for. But you can do a little bit more. What you can do is you can add this flag called -draftCompile, which was added to GWT 2.0. And if you do this, what the compiler does is it still does some optimizations, but it doesn't run them in a loop. So the compiler kind of, when it's doing the optimizations, it does an optimization pass, and then it says, well, if anything changed or if it got some kind of gain, let's try it one more time. And then if the code gets smaller, it's like, oh, let's go back through and run those optimizations again. And it will keep iterating until it can't squeeze your application down anymore. And what the draft compile says is, oh, only do the iteration once. So do a quick optimization pass, but don't keep going back trying to find more, squeeze out more and more. Here's a real-world example. I have a relatively large graphing library called Timescope, 300 kilobytes of code on disk. A production compile on my Mac Pro 4-core machine takes 3 minutes and 47 seconds. A dev compile with the module I showed you using draft compile takes 42 seconds. 42 seconds, I mean, it's still a lot, right? We'll try to improve on that. But that's like a 6 times, I don't know what it is at, 5 times, 6 times, 7 times reduction. It's pretty good. But for reference, a dev mode refresh to this app is 2 seconds. So don't do what I'm telling you. Well, do it because it does help, but don't really rely on it. Don't rely on doing full compiles if dev mode is available for you. You'll be a lot less irritated. However, we can go further. It turns out a Mac Pro is 2 times faster than a MacBook. Well, why should that be? The one I have at home versus my desktop, my Mac Pro, is the same CPU, same frequency. Well, the GWT compiler uses multiple threads. So the more cores you have, the faster it's going to be, and it farms those out. So buy a faster machine is one thing to do. If you have a RAID array, the compiler is relatively disk I/O hungry. So if you have a RAID array or an SSD drive, it does tend to produce a benefit. It varies. I've measured it to be about 50% on my machine. 64-bit Java 6 VM on the Mac. If I enable dash server when I'm running the GWT compiler, I get a 15% faster compile. And if I enable 2 gigabytes of memory and dash server, my compile is reduced from 42 seconds to 26 seconds. So it's going back 42 seconds, 26 seconds. That's pretty good. So use draft compile, use dev module, add more memory, add some more CPUs, and use dash server, and you can double your compile speed about. So there's one other thing you can do. GWT has this thing called generators. Some of you may be aware of it, but basically the compiler can execute a plugin sort of your own writing at compile time and generate code and then compile it. And this is how GWT RPC works. If you are willing to go the route of eliminating RPC and other generator-dependent libraries, the compiler will run faster. But don't do it unless you really have to, because you lose some productivity. Now, some of you are just a little bit more impatient, and 26 seconds for a compile is still too much. So if you got a little bit of extra money in your pocket, and you got a cluster sitting around in your home or maybe your place of business, or you can use you can sort of hack into a botnet into your coworkers' machines, you can use distributed builds. So this was added to GWT, but it wasn't really documented, but GWT does have the capability of farming out the compiles to a cluster. Now, the components for doing this are there, but the glue isn't, because we don't know what your internal network is, so we can't just write something that's going to distribute stuff out. because how your machines copy, what's your network look like? You got a SAN, network attached storage. We don't know that. So you have to write this stuff to sort of marshal this stuff around. That's the piece you have to write, but we'll provide all the other goodies. So the first step is you have to run a pre-compile. That's that first phase of the compiler. So let's imagine somewhere on your computer, on your corporate network, there's a shared network-attached directory called work. So you run this command, java com google gwt dev precompile, and you give it the name of your gwt module. And you give it -workdir and this network-attached directory. So the gwt compiler will do that initial parsing step, take the Java AST and kind of serialize it to that directory, and we'll write out an extra file called permcount.txt. What this says is how many permutations is going to be compiled. Like if you've got Safari, IE, Opera, and Firefox, it's 4. If you've got 2 different languages, it's 2 times that, so it's 8, and so on. So that will tell you how many permutations the compiler is going to compile, which kind of tells you how many machines you might want to maximally distribute it to. The second step is the slowest part of the compiler. This is the distributed. This is called the compile perms part. It's the highly parallelizable part. It's also the part that does most of the optimizations. So what we want to do is if you've got like n machines and you've got n permutations. Let's say you have 8 machines and you've got 8 permutations to compile. For each machine in your cluster, we're going to run this command com google gwt dev compile perms, and we're going to give it the module, hello module. You give it the same workdir you did to precompile, which is on your network somewhere, and you give it -perms I, where I is 1 to 8. So on the first machine, it's -perms 1, and on the 8th machine in your cluster, it's -perms 8. And that will map to some particular thing like English Firefox and Chinese IE or whatever you're compiling for. If you've got less than the number of machines and the number of permutations, let's say you have 32 permutations, but you only got 8 machines, you have to have some kind of queuing system that you built yourself, some kind of script where you basically have a list of the things that have to be built, the perms have to be built, and you dequeue the one, and when your machine's done, the next free machine will dequeue the next one, and so on. But you guys are really smart, and you'll figure that out. The final step is after all of the various permutations have been compiled, you're going to do a link stage. And what this does is it compiles all the generated artifacts, all the JavaScript files, all the sprited images, all of the HTML files, everything the gwt compiler produced, and it has to package them up. And the standard linker is going to package it for like war deployment. But I mean, there are other linkers out there people have wrote. You're deploying on an Android device and things like that. There's all kinds of fancy stuff you can do. And what you do is you run java com google gwt dev link, and you give it the module. And again, you give it the workdir. You give it the wardir, which is where it's going to deposit the war-structured application. And you give it this directory called aux, which is where to put files that you don't want to serve up from the war. Because the compiler generates various extra files like serialization policy things, the story of your compile, which is like what the compiler did to your code and where all this, what's taking the most amount of space. So you don't want that to be visible to the user. Now remember, the link phase, like the precompile phase, executes on a single machine. That's the serialized part. And also remember that the workdir, the gwt dev jar that has the gwt compiler in it, the gwt user jar, and all your application's source and other resources have to be network visible, because if you're going to farm this out to all your machines, they have to be able to see it. But that's basically it. Those 3 simple steps, and you guys will be building, doing builds in 1 or 2 seconds if you're fast. So here's that live notes link again, if you want to look at the wave where their notes are being taken. I think you can also ask questions there, but I'm ready to take questions, so if you want to, you can come up to one of the 2 mics, and I'll be happy to answer. Thank you. Or I can look in the wave. Maybe somebody already asked a question. Yes?
Yeah, could you talk a little bit more about the linking cycle? You mentioned that, is that going to like let you link modules together without necessarily recompiling all of them, in one big go, or whatnot? Just talk a little bit about it, I guess.
Okay, so the linking cycle is essentially responsible for a couple things. One is it generates the bootstrap script, so the .nocache.js script, which is different depending on where you intend to ultimately deploy your application. So for example, you know that there's the cross-site linker, which is if you've got a GWT application and you want to sort of source script it from a third-party domain, versus another linker we have called the iframe linker, where it actually kind of loads the GWT application up in a hidden frame. There are other linkers, like there is a gadget linker. So if you want to write an iGoogle gadget using GWT, there's a linker that's able to structure the code such that it can load up through a proxy server in iGoogle context. But essentially what the linker is supposed to do is it gets a list of artifacts, which are all the compiled JS artifacts, the files that are related to those, like PNG, sprited images, CSS that's been optimized or compiled, and things like that. And it basically has to put them in the right directory, so it's free to basically zip them up, put them in whatever directory structure it wants. And then finally, it has to generate the bootstrap code, because since it knows all of the output JS, it is the one responsible for generating the nocache.js file, which knows which correct permutation to actually load up. So it will say, if in the script, it will say, if you're on IE browser, then you have to load up this particular artifact, versus if you're on Firefox, it will load up this particular one. So the script does detection, loading, so it generates the nocache file, and it packages, essentially. Yes? Oh.
Thank you. You talked earlier about the obfuscation on the RPC data types.
Yeah.
I'm curious how that works, because your backend wouldn't know what the obfuscation was.
I'm actually not that, Bob Walter would know more exactly how it works, but I believe that there's a file written to disk that knows the map between the obfuscated name and the real name, so that when it gets a serialized payload on the server, it will look up via the obfuscated identifier what the real Java identifier was.
Okay, makes sense. Thanks.
Okay. Your turn?
Is there any way to avoid a full compile and run dev mode when you change things that are in the server package? I'm sorry, shared. If you know that the branch of code isn't going to be affected on the server, you're just doing front-end debugging, but it just happens to be a shared class. Yeah,
that's a good question. We've heard that a lot, and unfortunately there's no good answer for it, because sometimes if you run the server in debug mode, sometimes the VM can be told to reload a class that's been modified, and sometimes it can't. But we're working on a couple things to ameliorate that. We have something we're working on called super dev mode that sort of tries to eliminate what it tries to make the refresh in dev mode faster from the aspect of it has to run the generators every time, because something could have changed there. And also to sort of make the server-side reloading happen better. But I can't give you a direct answer for that, because we're still kind of thinking about how best to do it. But you might want to look at something called Java Rebel, if you've seen that. It's I believe it's a utility that you can use that allows you to reload any class at runtime on the server side. So I think people use it to get around the limitations of they change something in Eclipse. This is outside of GWT. It's like for any Java application where they can modify a class, and then they want to reload it, and a lot of times the debugger in Eclipse will say, well, it can't reload this class. You have to restart it, restart the server. But I think Java Rebel actually allows you to get around that limitation.
Do you know if that's applicable if you're running under no server, where you have your own deployment container?
Actually, it would be even more applicable, because then you would have more control over how the server gets started if you're running your own server rather than the dev mode server.
And then the name of that was again? I'm sorry.
I think it's Java Rebel is the name of it. I could be misremembering, but.
Thank you.
I'm curious about turning off the Java class data, disabling it.
Yeah.
If I turn that off and another developer does an instance of, is it always true, always false, or does it throw an error?
It still will be able to do instance of correctly, because the way that GWT implements instance of is by this hidden field that it puts on the prototype of every object called the type ID. So the instance operator operates on that. The class metadata is really just kind of string data that is really for display purposes, and it's not actually, it doesn't really matter too much to the logic of implementing the instance of operator.
So you lose the class like toString on the class?
Yeah, if you toString the class, instead of being like, employee, it would be like class $1 or something like that.
You mentioned that the singleton pattern implemented with a static initializer is slightly inefficient in GWT because of static initializer.
Yes.
What if you use the enum pattern for singleton as opposed to a list of constants, because there's that other issue with the enum. Which
Yeah.
one's better?
It's still inefficient. So anytime you have a static field that is initialized by a static initializer, and an enum is an implicit static initializer, it's always there. However, we do have two optimizations that are in the pipeline that both reduce the cost of static field initializers by tracking if an initializer has been called once, then later in the code, it won't call it ever again. So it reduces the amount of times it's going to check. And then secondly, and a lot of times we can actually hoist those initializations up to the front of the program so that after the program's been bootstrapped, right, basically no initialization happens at all. So there are a lot of things we have in the pipeline. So I don't want to encourage people too much to change their code. Only, until GWT 2.2 or whatever comes out, if you're really desperate, you can look at like changing fields from static to being lazy evaluated.
All right, thanks.
Okay. I got 4 minutes left if anybody has any questions. Otherwise, thanks for coming. Oh, and by the way, advertisement. The next session, you definitely want to stay around for it. It's architecting GWT apps for performance. And it's done by Joel Weber and Adam of the Wave team. So you definitely want to stick around for that because they're going to teach you a lot of the tricks they use to make Wave run fast. Thank you.